Hello, folks. Welcome to the screencast. So, I have some very exciting news to share with you guys. So, I've decided to go solar and install some solar panels on my house. And the dilemma that I'm immediately faced with is to which roof for which surface among these four different roofs should I install my solar panel on. So, assuming I have this nice big house which has this multi-hatcheted roof, and let's say this part is facing the south, so this is my south facing part, and the opposite side of this would be my north facing part. Similarly, this part of my roof is what is facing the west, and this part is what is facing the east. So out of this four possible choices, where should I install my solar panel? And the answer really depends upon where do I live. And let me illustrate why. So I'm currently living here in the northern hemisphere, and Bay Area, it has a latitude of approximately 37 degrees. So now if I'm living in the northern hemisphere and my house, just for the purpose of it's located this. So what I want now to do is I want to have this panel essentially facing the sun. So I have my sun located somewhere over here, and then I have these photons or these light coming from the sun in this particular direction. So now what I want to do is to optimize the efficiency of my panels. I want to essentially have this panel facing towards my panel, which is located over here. This should be facing the sun. So this would happen if I'm located in the northern hemisphere, then I should place my panel on the south facing part of my roof. Similarly, if I'm located in the southern hemisphere, I should place my panel on the north facing part of my roof. And the optimal angle at which this roof, or this ideally this panel must be tilted, is essentially equal to the latitude of this place. And to prove that this panel is in fact facing the sun, when I tilt this roof at an angle of the latitude. Let me illustrate this further so there's no confusion. So let's say I'm at an altitude of theta, and then this is essentially my direction of my roof if I have no tilt. So this is my house, and if I have no tilt, then this is the direction. Now if I tilt this further in an angle of theta, so my panel is essentially facing this particular direction. And if I choose this to be theta as well, so I have this angle to be 90 degree, right? And if I have this angle to be theta, then this angle would be 90 minus theta. So if I connect this line over here, then if I look at this bigger triangle ABC, so now I can see that this angle is theta and this angle is 90 minus theta. So this angle essentially now must be 90 degree, or this panel is facing this direction of the incoming sunlight or the radiation from the sun. So that's why then it makes sense to essentially orient your roof, or the angle of your of this tilt should be theta as well. And as you can see, this is facing the south if I'm in the northern hemisphere. Similarly, if this house was located over here, then I would choose the opposite roof. So I would choose essentially the north facing part of my roof. So now the optimal direction, as I just determined, it's equal to the latitude. So if I'm living in the Bay Area, latitude is 37 degrees. So this optimal tilt would be 37 degree, and I'll choose the south facing part of the roof. But many times you can't choose really the angle of the roof unless you're designing a new house. So let's say you're buying an old house and it has maybe a higher angle, or it has a lower angle over here. So you can still get around that. So you still, if you are living in the Bay Area, which is the northern hemisphere, you choose again the south facing part of the roof. And if you are at a higher angle, you can add a fixture over here such that your solar panel is placed in this particular manner, such that this angle is again equal to the latitude, which is 37 degrees. Similarly, if you have a lower tilt on your roof, you can add a fixture over here before placing the panel and still get that optimal angle. This will of course add this fixture. This fixture would add to the cost of your panel, but we'll discuss about that later. So if you get lost, if you lose your GPS and you need to find directions, a good way to would look at that if to look at the nearby houses, and if they happen to have solar panels installed, then you can look at which side or the roof which is essentially the solar on which the solar panels are installed should be the south facing direction. So if you get lost, this should essentially be the south facing direction. And if you get even lost, you were flying somewhere and you had a plane crash, something similar to what happens in Lost, and you wake up in a desert with these solar panels. So you want to figure out, and these solar panels, they're at a fixed angle, and you want to figure out how far away are you from the equator. So you can look at the tilt of these solar panels, and that should essentially give you the latitude, if hopefully these people have installed these panels in the right way. So this is assuming this optimal tilt is assuming that I have the sun shining perpendicular. I'm at the noon time where the sun is exactly shining at the top. But in reality, the sun, if I'm located on the earth, the sun will essentially rise. It would rise in the east and settle in the west. So there's a direction of motion associated with that. Another thing which we should need to take into account, which makes this even more complex, is that the earth is tilted with respect to its axis of rotation. So we all know that earth is essentially tilted at an angle approximately 23 degree with respect to its axis of rotation. So let's say at a point in the northern hemisphere, so when it's during the summertime and it's summer solstice, so this angle at which my panel should now face towards the sun is now reduced. Similarly, when I go into it's reduced by this angle of the tilt. So if I had essentially I was a latitude of theta, so this angle now, the optimal angle, is actually theta minus my tilt angle. And if I go in the winter, then its optimal angle is theta plus 23, which is adding this angle to the tilt. So now that we have discussed the phenomena of day and night and the tilt of the earth, it's a good point to introduce the need of the tracking. And to introduce the need of the tracking, what we can do is look or think from the perspective of these mere mortals or human beings who are living on the planet, and for us, this is how all this motions, all these interplanetary motions manifest into how do we perceive the sun. So every day the sun essentially it goes around, or actually the earth is going around, but looking from the perspective of this mere mortals, the sun is going around. So our panel needs to track this motion of the sun every day. And then I have this I have this optimal angle which corresponds to the latitude. In this case, it's a latitude of 55 degrees, but this only occurs during the months of the equinox. So this would be the months of March and September if I'm living in the northern hemisphere. Then during the summer, that's in the month of June, if I'm in the northern hemisphere, I'll see the optimal angle to be reduced by the angle of by the tilt of the earth, which is 23 degrees. And if I go in the winter, then I'll see my sun is essentially it's rising at much higher tilt, and I have this tilt angle to be added by this optimal angle, which needs to take into account this additional angle coming in from the tilt of the Earth. So that is why if you design an optimal tracker system, you often track these two axes. So you track the motion of the sun every day. So that's one axis for that, and the other one is to track the tilt of the Earth. So this axis tracks the tilt of the Earth.